Welcome back to the workshop. We're going to continue taking a look at a knapsack problem. But in order for us to address the knapsack problem as best as we can, we have to talk about sets. So we'd like to give a nice introduction to sets and give a couple ways in which we can denote sets. So a set is really just a collection of items or objects. When we have a set full of whatever objects are in there, each of the objects in the set are called elements of the set. So you will hear them referred to as elements rather than objects or items. All right, so a set is usually denoted by a capital letter. So for example, S, as we have here, and if some item is an element of that set, then we would denote this by saying that the item belongs to the set. Okay, so X is an element of the set. X belongs to S. So S is a set. X is an element of that set. Okay, so X is just some object, and it may or may not belong in the set. We'll take a look at some examples in just a moment. So let's see here. If we have another object, Y, but it's not an element of the set, we could also denote that kind of like how we say two things are not equal, then Y is not in. So we would say it's in, but wait, nope, it's not in S. So the belongs to symbol with a line through it. So an object that is in the set, an object that is not in the set. An object that is in the set is called an element of the set. All right, so we have a couple different ways to represent sets. So we're going to take a look at some examples of sets here. And in the first example, we will consider how to write one way to represent sets. And then in another example, we'll consider an additional way to represent sets. All right, so let's take a look at a set that contains automotive manufacturers. So we'll call it A. And let's go with the big three for American manufacturers. So we've got Chevy and Ford, and we'll just call it Dodge. That makes the most sense, right? Chevy, of course, has a bunch of other companies as well. That's Buick, Cadillac. I think I recently heard that Subaru is actually officially a Chevrolet product now as well. So that's kind of interesting. Anyway, a discussion for later. Ford, of course, is Lincoln and Mercury. Do they make Mercuries anymore? I don't even know. And then Dodge, of course, we have Chrysler along with that as well. So the big three, they represent several different companies. But anyway, so we can see here that Chevy is in the set A. However, maybe you're a Honda fan and you would notice that Honda is not in the set A. Okay. Let's consider a set that contains people. So P for people. So A is this set. It can be referred to as A. P is our next set. And let's go with my family. So me, my wife, and my son. Excellent. And then let's take a look at a set that contains numbers. So let's call it, let's go with G. And here we have 6, 17, and 47. Just a few numbers. So again, here we note that maybe 6 belongs to the set G. But a number that does not would be 12. 12 does not belong to G. So just examples of notation. And then the integers. So the integers have their own special notation. That is the Z. So the integers are the collection of numbers. So sometimes we have an infinite list. So the integers, of course, include 0, 1, 2, 3, 4, but then you'd like to keep going, so you just put ellipses. But the integers also include all of the negatives, so we would have -1, -2, and we can actually put ellipses on this side as well, which tells us that it extends in both directions. Excellent. So this is how we can use curly braces or curly brackets to give a set by listing the items. Okay, listing the items. If you're not familiar on how to draw the curly braces, you can consider drawing an S over a 2 and a 2 over an S to get your left and right curly braces. All right, so let's consider another way to write automotive manufacturer, another way to write lists, or not sets, there we go, a way to write sets. So this additional notation is called set builder notation. And if I wanted to consider all automotive manufacturers, I could simply say the set C, which is, we'll still use curly braces, but we would say X such that, okay, so the vertical bar is such that, so objects such that the object is an auto manufacturer. Now Honda would belong to that because Honda is an automotive manufacturer. Cool. So this one is kind of, maybe just a little bit weird, right? It's not numbers. So let's take a look at one that is numbers. So let's look at H. Now, sometimes it's important to say where these things are coming from in the first place. So in our first example, we said X, these objects are automotive manufacturers. Okay, cool. Maybe not the most descriptive thing ever. But we could write it as X such that X for real numbers that are less than 5 but greater than 1. We could say X belonging to the real numbers and so X such that X is a real number between 1 and 5. Now, I could have written this a little bit differently as well. You'll find that in many cases, you would say where it belongs on the left side of the vertical line here. So this fancy R is the real numbers. Maybe I should write this one a little bit better. Real numbers. So when I read this first line, I'm saying all objects such that that object is a real number and that that real number is between 1 and 5. Here I have all X is a real number such that X is between 1 and 5. So they say the same thing. I want all objects where that object, right? All objects such that that object is a real number and it's between 1 and 5. Or I could simply say, I want real numbers such that the real numbers between 1 and 5. Again, they say the same thing. All right, let's see here. Solutions to a polynomial. Excellent. So there are a couple different ways that we could write this. If you want only the integer solutions to a polynomial, you might say that X belongs to the integers. So that way we know we're looking at integer solutions to a polynomial. X minus 6 times X minus 17 times X minus 47 is equal to 0. So I gave it in its factored form, so it's easy to see the solutions. So this is just saying it's the set of integers as long as it satisfies this equation such that this equation is equal to 0. So I'm looking at the numbers 6 because 6 minus 6 is 0, making all of this 0. I'm looking at 17 because 17 minus 17 is 0, making all of this 0. And 47 minus 47 is 0, making all of this 0. So those are my three solutions to the polynomial. So I'm looking at those three integers. I could also look at the integers greater than negative 24. So let's call that S. And I'm looking at the integers, x belonging to the set of integers. So I know I'm pulling out an integer. What integers am I pulling out? Which ones are included in this set? Well, the ones that are greater than negative 24. So that's set builder notation. That's very nice. So one set that we want to make sure we mention specifically is the empty set. The empty set can actually be denoted in two different ways. The standard way is like that. So a 0 with a line through it, or an O with a line through it. Okay, that is the empty set. It can also be denoted by listing all of the elements in the empty set. Well, the empty set has nothing in it. So when I list them, there's nothing there. So this is the one that will appear in the text. This one you might see referred to in other places as well. But both of those refer to the set that contains nothing. And that's a valid set. The set that contains nothing is a set. What does it contain? Nothing. Excellent. So that's our brief introduction to what a set is and how we can represent them. We will continue by taking a look at relationships between sets and the ability for us to perform operations on sets. Set operations we'll take a look at, I guess, a little bit later in another section, but we want to take a look at a little bit of the relationships in this section yet. So I'll see you guys back in the workshop for more on a knapsack problem.